Today we'll be discussing maximum shear stresses in 3 dimensions. As you know that this is a very important issue in strength of material and design, because when we design, we not only look at the principal stresses, we also look at the maximum shear stresses. And you may remember that for designing for ductile materials, maximum shear stresses are considered for ED. And I have shown here a typical Morse cycle for you to remember that in a 2D case, we have two principal stresses, sigma 1 and sigma 2, and two maximum shear stresses, positive and negative, because positive and negative, and they are given by sigma 1 minus sigma 2 by 2. So that was a very simple thing, and we have learned that in strength of material. But in 3 dimensions, things are a little different. And you will see that there are many more planes of maximum shear stresses. In fact, there are 12 planes of maximum shear stresses, and we'll discuss how this comes into picture. So we go on to the main discussion. Here, we first remind ourselves of the initial discussion that we had. That was to show the stresses at a point on a cube, the 9 stress elements or the 6 stress elements. And we took a inclined plane or cut a tetrahedron from there, and we showed the stresses developed on the inclined plane, which balances the stresses on the other 3 faces. And the resultant stress was sigma dash that was resolved into along the normal and along the plane, sigma n dash and sigma s dash. Sigma n dash is the normal stress and sigma s dash is the shear stress. We also resolved that resultant stress along the coordinate axis, that is sigma x dash, sigma y dash, and sigma z dash. And that is shown in equations A and B. That is very simple, and we have discussed it many times. So what I want to discuss here is that when we derived the normal stress on the inclined plane and equated it to 0, we have found out the maximum or the minimum value or the stationary values of the normal stress. In fact, what we did by doing that is that we have rotated the inclined plane in different inclinations, and we have found a point where on that plane there is no shear stress, and the values were normal values of normal stresses were maximum or minimum. So that was given. The condition for maximum and minimum values of the normal stresses on the oblique plane were given in terms of an arbitrary value sigma, which later we found out that was the eigenvalue of the characteristics equation. And there we showed that the sigma x dash is equal to sigma L, sigma y dash equal to sigma ym, and sigma z dash equal to sigma n. Now, instead of the Cartesian coordinate that we assumed before, if we rotate the element, which is as good as rotating the inclined plane, then we'll get a position where on the faces there are no shear stress. So those are the planes of maximum or minimum normal stresses or the principal stresses. So now if we align the coordinate axis along the principal axis or the planes or the axis perpendicular to the principal planes, then we can write sigma x dash as sigma 1L, sigma y dash is equal to sigma 2n, and sigma z dash equal to sigma 3n, because these are the three principal stresses. And the three principal stresses will be along the 1, 2, and 3 axis when we have inclined the body. Okay, I'll repeat this once again. We have found out there that the condition for the maximum or minimum values of the normal stress, which we call stationary values, on the oblique plane was given in terms of arbitrary stress sigma. So there we have showed that the sigma x dash equal to sigma L, sigma y dash equal to sigma m, and sigma z dash equal to sigma n. So that was with respect to the Cartesian coordinate that we have assumed x, y, z. Now when we rotate this and find out the principal axis, then if we align the coordinate axis with the principal axis, then we can replace this sigma with sigma 1, sigma 2, and sigma 3, because this is no more unknown, because we have rotated the inclined plane or the cube in such a way that there is no shear stress and only principal stresses are there on the faces. Okay, so here from equation C tells you that sigma x dash can be written as sigma 1L, sigma y dash can be written as sigma 2n, sigma z dash can be written as sigma 3n, only when we align the coordinate axis with the principal axis. Okay, so with this, things becomes much easier because we don't have to take the 9 stress elements. We can deal with only 3 stress elements. So the normal stress, what we have seen before, I'll just show you again. Normal stress was sigma n dash sigma x dash L, sigma n dash equal to sigma x dash L, sigma y dash m, sigma z dash n. And if we replace sigma x dash by sigma 1L, sigma y dash sigma 2m, sigma z dash sigma 3n, then equation A will become equation D, because we are replacing sigma dash with sigma 1L. So it will be sigma 1 L square, sigma n dash will be sigma 1 L square, sigma 2 m square plus sigma 3 n square. Okay, if you just look back, it will be very clear. What we have done is we have replaced sigma x dash by sigma 1L, sigma y dash with sigma 2m, and sigma z dash with sigma 3n. And we got sigma n dash equal to sigma 1 L square, sigma 2 m square, sigma 3 n square. Similarly, if we replace the values from equation C and into E, we'll get an equation like this. That is also very simple. What we are doing is we are putting the values of sigma x square, that is sigma 1 square L square, sigma 2 square m square, plus sigma 3 square n square, minus sigma n, which is this. So all we are doing is we are writing sigma n dash as in terms of sigma 1, sigma 2, sigma 3. So this is equation F, and we have simplified this, and it becomes a very handy equation, which is sigma 1 minus sigma 2 square L square m square, sigma 2 minus sigma 3 square m square n square, plus sigma 3 minus sigma 1 square, n square, L square. So sigma s dash square, it is easy to write it in terms of square rather than squaring. Sigma s dash square from E, if we substitute equation C into equation E, we'll get sigma s dash square equal to sigma 1 square L square, sigma 2 square M square plus sigma 3 square N square minus sigma N square. And sigma N square is sigma 1 L square plus sigma 2 M square plus sigma 3 N square whole square. And if we simplify this, it will come down to a very nice handy equation. That will be sigma 1 minus sigma 2 square L square M square plus sigma 2 minus sigma 3 whole square N square plus sigma 3 minus sigma 1 square N square L square. Okay, so these few equations are very important for our next steps. So remember what we have done here, we have converted the equations in terms of the principal stresses. Okay, so now we want to find out the maximum shear stresses. So what would be the next step? Next step would be to differentiate sigma x dash square. Instead of sigma x dash, we take sigma x dash square, because otherwise it will involve taking the roots of this, that will involve more complications. So we differentiate sigma s dash square with respect to L, M, N. But there is no need to differentiate with all the three, because there is a relation between L, M, and L square plus M square plus N square is equal to 1. So we need to differentiate only with two, L, M, or M, N, or L, N. So we first take L and M, and for the stationary or the maximum or minimum values of sigma s dash, we derive sigma s dash square with respect to L and M. If you look at equation F, it is very easy. Derive this with respect to L, you will get 2Lm square sigma 2 minus sigma 1 minus sigma 2 square minus 2Lm square sigma 2 minus sigma 3 whole square plus 2L minus 4L cube minus 2Lm square multiplied by sigma 3 minus sigma 1 whole square. This will be equal to 0, because we are trying to find out the maximum or minimum value. Similarly, we derive this with respect to M. If you look back, equation F, especially the last line, you will see it will be very easy to see that del sigma s dash square by del M is equal to 2M L square sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square 2M minus 2ML square minus 4M cube minus 2ML square sigma 3 minus sigma 1 whole square is equal to 0. So we have got two conditions, G and H. And these two conditions will give us the conditions for maximum or minimum shear stress. Now, these two conditions must be satisfied simultaneously. So how do we do it? Let us look at equation G first. Equation G will be satisfied if we take L equal to 0. That is very simple, because there is L in all the parts, all the components. L is here, L is here, L is here. So if we take L equal to 0, then equation G is satisfied. Okay? What does it mean? you put L equal to 0 into H, you will see everything is 0 except 2m minus 4m cube, because L is here. Only this component or this term is remaining. And even in this, 2ml square is 0. So we are left with 2m minus 4m cube. So we have got, from putting L equal to 0 in H, we have got 2m minus 4m cube equal to 0. Now, so what does it mean, 2m minus 4m cube? It means you take m out, so either m can be 0 or 1 minus 2m square can be 0. Take m out, what do you have? M into, take 2m out. So you have got 1 minus 2m square. So either 1 minus 2m square is 0 or m is 0. These are the only two possibilities. So look at it carefully. If we have L equal to 0, then we have got m is equal to 0 or 1 minus 2m square is equal to 0. If L equal to 0 and m equal to 0, then we have got L square plus m square plus m square equal to 0, so, is equal to 1. So then n must be 1. Look at it carefully. We are saying L equal to 0. If L equal to 0, one possibility is m equal to 0. If both L and m is 0, then n must be 1, because L square plus m square plus n square is equal to 1. Okay? The second possibility is that if L equal to 0, then 1 minus 2m square is equal to 0. So there m is equal to plus minus 1 by root 2. So that will apply here. If L is equal to 0, the another possibility is m equal to plus minus 1 by root 2 and n is equal to plus minus 1 by root 2. Now among these two solutions, if you look at it carefully, you will see that this n equal to 1 defines that it aligns with one of the principal axes. So this is the principal plane. The first condition, because you remember when you derive, you get either the maximum or the minimum condition, or the two conditions. The first condition tells you that it is a principal plane, and the second condition is the maximum shear stress plane. So how many maximum shear stress planes are there? Actually, there are 6, and there are 4 planes of maximum shear stress. Plus minus here, plus minus here. Now, in the same way, here we have derived with respect to L and M. We can do in the same way, we can take L and N or M and N. And that way, we can have 3 conditions. We can have L equal to 0, M equal to plus minus 1 by root 2, N equal to plus minus 1 by root 2, or when M equal to 0, L equal to 1 plus minus 1 by root 2, or N equal to plus minus 1 by root 2. And when N equal to 0, in the same way, we have got L equal to plus minus 1 by root 2, and M is equal to plus minus 1 by root 2. So how many planes we have got? If you look at it carefully, we have got 12 planes of maximum shear stress. So what we have done, I'll just go through it again, go back. We have written the shear stress on the oblique plane in terms of principal stress and the direction cosine. That is in equation F, and it is very simple. If you substitute equation C from here into E, you will get this equation. And on simplifying, this becomes sigma 1 minus sigma 2 square L square m square plus sigma 2 minus sigma 3 square m square n square plus sigma 3 minus sigma 1 square L square m square. So to find out the maximum value of the shear stress, what we have to do, we have to derive this or differentiate this with respect to the direction cosine. We derive with respect to differentiate with respect to direction cosines because we are rotating the or changing the position of the inclined plane and finding out in which plane the value is maximum. Okay, so we do that. Now, as I said before, that there is no need to derive with respect to all the three direction cosines because there is a relation between the three. So if you do only two, that will be satisfied. So we first take L and M and we derive with respect to L and M. So del sigma S square by del L. And if you look at it in the previous equation, you will see that it comes down to 2Lm square sigma 1 minus sigma 2 square minus 2Lm square sigma 2 minus sigma 3 square plus 2L minus 4L cube minus 2Lm square sigma 3 minus sigma 1 square equal to 0 because we are trying to find out the maximum and minimum position. In the same way, if we differentiate sigma s square with respect to m, we get equation H, which is ml square, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square, 2m minus 2ml square minus 4m cube minus 2ml square sigma 3 minus sigma 1 square is equal to 0. Now, to find out the maximum value, both these equations G and H must be satisfied simultaneously. So how do you do that? As I said before, look at equation G. If you take H equal to 0, then equation G is satisfied. Put that value in H because we have to satisfy it simultaneously. If we put H equal to 0 in equation H, we'll see that everything else is 0 except 2m minus 4m cube because this term is also 0. So 2m minus 4m cube equal to 0 from H. So one condition is that, and the 2m minus 4m cube can be written in terms of as two conditions. If you take 2m out, you have got 1 minus 2m square, and m is equal to 0. This is equal to 0 if either m equal to 0 or 1 minus 2m square is equal to 0. Look at it very carefully, you will see it's very simple. This is equal to 0 if either m equal to 0, because you can take the m out, or 1 minus 2m square equal to 0. So one condition is if L equal to 0, m equal to 0. If L equal to 0 and m equal to 0, then n must be equal to 1 because L square plus m square plus n square is equal to 1. Okay? The second condition is if L equal to 0, then m is equal to, you take this condition, this means m is equal to 1 by root 2. So if L equal to 0, second condition is m equal to plus minus 1 by root 2, and n will also have to be has to be 1 by root 2. Now, if you think carefully, you will see that the first condition applies to principal plane, and the second condition applies to maximum shear stress. So the maximum shear stress conditions are L equal to 0, L equal to 0, M equal to plus minus 1 by root 2, N equal to plus minus 1 by root 2. If you look at it carefully, there are 4 planes. And similarly, instead of L and M, if we take M and N or N and L, you will get 2 more conditions, and there will be M equal to 0, L equal to plus minus 1 by root 2, N equal to plus minus 1 by root 2. And again, similarly, you can get N equal to 0, L equal to plus minus 1 by root 2, and N equal to plus minus 1 by root 2. So if you look at this condition or equation K, you will see there are 12 planes of maximum maximum shear stresses. So compare this with the 2D situation, which I showed you in the beginning, that in the 2D, you have got only 2 planes of maximum shear stress. But here you have got 12 planes of maximum shear stress and 3 planes of principal stresses. Okay, so now we go to the next point. Now, we have seen that the maximum shear stress can be given by sigma 1 minus sigma 2 square, L square M square, plus sigma 2 minus sigma 3 square, M square N square, plus sigma 3 minus sigma 1 square, N square L square, whole to the power half, because that was sigma S square. I'll just flash back and show you equation F. Equation F was sigma S dash square, and this was in square. So all we do is to take the square root of this. So we have got sigma S dash equal to sigma 1 minus sigma 2 square, L square M square, sigma 2 minus sigma 3 square, M square N square, plus sigma 3 minus sigma 1 square, N square L square, whole to the power half. It's very easy to remember. There is a sequence. If you see sigma 1 minus sigma 2, L, M, sigma 2 minus sigma 3, M, N, sigma 3 minus sigma 1, N, L. And they're all squared and then taking the root of it. And sigma N dash is again sigma 1, L square, sigma 2, M square, sigma 3, N square. I'll flash back and show you. This is what we got in equation D. So if you take equation D and F, we get this. So the first equation is for shear, and the second equation is for normal strain. Now what does it mean? In the planes of maximum shear stress, there are normal stresses, but in the planes of principal stresses, there are no shear stresses. Do you understand? I'll show you back. If you see this figure, in this figure is the orientation of the cube for principal stresses. On this cube, on the faces, there are no shear stresses. But if you take the 2D situation, on the planes of maximum shear stresses, there are principal stresses, because the distance of this point from the origin is the normal stress. So what I'm trying to say is that in the planes of maximum shear stresses, which is 12, there are normal stresses. So how do you find out? We have seen that there are 3 sets of direction cosines, and if you simply put them here and here, you will get the values of shear and normal stresses. That's what I've shown here. If n equal to 0, m equal to plus minus 1 by root 2, n equal to plus minus 1 by root 2. If you put it here, you will get sigma s dash equal to plus minus sigma 2 minus sigma 3 by 2, and sigma n dash, which is the normal stress, equal to plus minus sigma 2 plus sigma 3 by 2. So shear stress is minus sigma 2 minus sigma 3 by 2, and normal stress is sigma 2 plus sigma 3 by 2. That is also very simple from 2D. If you look at the Mohs circle, the 2D, what is maximum stress? Sigma 1 minus sigma 2 by 2. And what is the normal stress? Normal stress is sigma 1 plus sigma 2 by 2. Okay, remember this? So in the same way, we have got the shear stresses as sigma 2 plus minus sigma 2 minus sigma 3 by 2, and normal stress as sigma 2 plus sigma 3 by 2. Okay, and in the same way, for other two conditions, if we put the values in these two equations, you can get the values of shear and normal stresses. Sigma S dash equal to sigma 3 minus sigma 1 by 2. You will see that since m is 0, we are talking about 3 and 1, L and n. Sigma 3 minus sigma 1 by 2, and sigma n dash equal to sigma 3 plus sigma 1 by 2. And similarly, for the last set of direction cosines n equal to 0, we get sigma S dash equal to sigma 1 minus sigma plus minus sigma 1 minus sigma 2 by 2, and sigma n dash equal to sigma 1 plus sigma 2 by 2. So what does it all mean? It all means is that just as we have got planes of principal stresses, we have got planes of maximum shear stresses. In the planes of principal stresses, there are no shear. That is a condition for principal stresses. But in the planes of shear stresses, there are normal stresses. And these can be found out simply by substituting the values of the direction cosines in these two equations. Okay, so it is very easy to find out for a set of conditions what is the principal stress and what is the maximum shear stress. So I'll go to a small problem to demonstrate this. Before that, I wanted to have a pictorial view of the shear stresses. This is a tetrahedron, and there are three faces with three faces with the three sets of conditions, and you will see that it all comes together as 12 planes of maximum shear stress. Okay, this you can see later, and now we'll go to a small problem. Now look at this problem carefully. The state of stress at a point within a stress body is given below. This is the state of stress. Find the normal and shear stresses on the plane equally inclined to the coordinate axis. So here he is giving you the LMN. How? Because he is saying that they are equally inclined to the coordinate axis. That means L, M, N are equal. So if L, M, N are equal, and we know that L square plus M square plus N square equal to 1, then L equal to M equal to N equal to 1 by root 3 is equal to is missing here. Now, if you look back or remember that we have written these four equations, which are very important. First, equation 1 gives you the normal stress on the inclined plane in the x direction in terms of the original stresses, sigma x tau xy tau xz. Then the component of the resultant stress on the inclined plane in the y direction was given in terms of stresses in the original planes, tau xyl, sigma ym plus tau yz n. And similarly, component of the resultant stress on the inclined plane in the z direction was given in terms of tau xzl plus tau yzm plus tau zn. So these three equations we have already seen before, and also we have seen that if we resolve sigma x dash, sigma y dash, and sigma n dash, z dash along the normal, then we get equation 4. So if we combine equation 1, 2, 3, and 4, we get sigma n dash. All you have to do is do simple algebra. You will see that sigma x l square, sigma y m square, plus sigma z n square, plus 2 tau xy lm, plus tau yz mn, plus tau zx ln. It's a very simple derivation. You can do it yourself. From this, you substitute 1, 2, 3 in equation 4, and you will get this. And if you put the values of the stress components and 1 by root 3 for LMN, you will get this value, 104.7 megapascal. These are all in megapascal. Now you want to find out the maximum shear stress. So maximum shear stress, again, is given in terms of sigma x dash, sigma y dash, sigma z dash, and sigma n dash. So find out sigma x dash from here, sigma y dash from here, sigma z dash from here. So if you do this small arithmetic, you will find that it comes out like this. And sigma n dash is already known. So you put that here from here, and you will get square as 7396, and square root will be 86.77 megapascal. Okay, so these are the maximum and maximum shear stress and we have normal and the shear stresses on a given plane. Okay, on a given plane there will be only 2. Remember this, on a given plane there won't be 12. The 12 is all together. If you take a given plane, there will be only 2. So if you take the square root of this, you'll have a plus and minus value. So it will be plus 86.7. Now this is clear? Or shall I go back and repeat it again? The question is, stress matrix is given. All you have to do, and they have also given you hints for the direction cosine. How they have given? They have said that the plane is equally inclined to the coordinate axis. What it means is he is inclining the oblique plane in different direction. For a given direction where L, M, N equal to L equal to M equal to N, and obviously where square M square N square equal to 1, then L, M, N equal to 1 by root 3. So for this condition, he is asking you to find out the normal and shear stress on the plane. So very simple. First thing is to remember that the equation 1, 2, 3, which we have derived earlier, and the equation for sigma n dash and equation for sigma s dash. So sigma x dash, sigma y dash, and sigma z dash can be easily found out if we know the sigma x, sigma y, sigma z, and the stress matrix. and 11. Just substitute this, you will find, substitute this, you will find sigma y dash, substitute this, you will find sigma z dash. And sigma n dash is sigma x dash L plus sigma y dash m plus sigma z dash n. So substitute these values into n, into this, and you get sigma n dash. So you get, you can either get the values of sigma x dash, y dash, z dash separately and substitute it here, or put it in this equation and get an equation for the whole thing. I've written the equation for the whole thing. If you substitute this here, you will get this equation. Or you can do it separately. You can find out sigma x dash, sigma y dash, sigma z dash, and substitute it here numerically. In whichever way you do it, you will get 104.7 megapascal. Check it. Then sigma s dash squared is again sigma x dash squared plus sigma y dash squared plus sigma z dash squared minus sigma n dash squared. I think by this time you must have remembered these equations, because these equations are very vital for doing any solid mechanics problem. So these are very easy. And if we find out the values of sigma x dash from here, sigma y dash from here, and sigma z dash from here, and substitute it here, and sigma n dash we already know here, we'll find out it comes out to 7396. And you take the square root of it, and it becomes 86.77 megawatt. Actually, it should be plus minus. Now, I just want to remind you one thing, that there won't be 12 on a given plane. There will be only 2. So there are 2 values. Okay, this problem is okay. Look at it again, and if there are any difficulty, we'll discuss it later. Let's go to the next problem. The next problem is the state of stress given below. For the state of stress given below, find the principal stresses and the maximum stresses. Now the state of stress is given very simple. This is in whatever unit, megapascal or whatever. Now the characteristics equation for finding out the principal stresses is here. Sigma 3 minus J1 sigma square plus J2 sigma minus J3 equal to 0. This equation, you look back in lecture 4, you will find out. So all we have to do is to find out J1, J2, J3. What is J1? J1, again, you can look back and find out. It's sigma x plus sigma y plus sigma z, and that is equal to 3. Square bracket is missing here. Similarly, J2 is sigma x, sigma y, sigma plus sigma y, sigma z, plus sigma z, sigma x, minus tau xy square, minus tau yz square, minus tau zx square. If you put the values here, you will get minus 6. Similarly, Z3 is sigma x, sigma y, sigma z, plus 2 tau xy, tau yz, tau zx, minus sigma x, tau yz square. Easy to remember, if it is sigma x, it will be tau yz, minus sigma y, tau zx, y zx square, minus sigma z, tau xy square, z xy square. If you put the values from here, you will get minus 8. So put this in the, this is called the main equation or the characteristics equation. By solving this, you will get 3 roots, and these 3 roots are the principal stresses. So when you substitute this, you get an equation like this, And if you find out the roots, there are many different ways of finding out the cubic, solving the cubic equation. The best way is to write a small program, or there are Newton-Raphson method or many other methods. I leave it to you to find out. If you can't do it, then we'll discuss it some other day. So if we solve this cubic equation, we'll get sigma 1 is equal to 4, sigma 2 is equal to 1, and sigma 3 is equal to minus 2. And maximum shear stress, as we know, are sigma dash S dash square is sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 3 by 2 equal to 3. And then give you 1.5, 1.5, and 3. So these are the, actually if you take plus minus, you should take plus minus. So these are the main values, and you take the plus minus values wherever needed. So these are the principal stresses, and here these are the shear stresses. Okay, maximum shear stress. So this is a simple 2 problems to solve. Read it carefully, and if there are doubts, we'll discuss it later. Okay, so that's the end of this note today.